confused this year, but they promised that if I explain my point well, they can change next year. So I have some hope. Applying for government when people have results. Pardon? I don't care whether you are negative or not. At least I won't teach people who think that they were given a course they don't like, because they would have applied when they have the results. If they just chose to do government because it's government, that's their problem. But all of you, some of you are given that's the choice they gave you. Some of you, even the teacher is the one who just put. And you say, I got the education by surprise. Your group maybe is special because you are very few. But most of the people get that problem. So we are now on the coefficient of coupling that keeps the marriage together. Coefficient of coupling, which is denoted by K. So take a circuit or coil 1. Take a circuit or coil 1 in which a current I1 is flowing, in which a current I1 is flowing. When this current changes, then it causes a flux in the same coil. So then the flux phi due to coil 1 in coil 1, that is 1, 1, is equal to L1 I1, which comes from the Faraday's law when we have the currents, where L1 is the coefficient of self-induction or self-inductance, is the coefficient of self-inductance, self-inductance, I think. Self-inductance. Now, if you have a neighboring coil in the neighborhood, so in the neighboring circuit 2, if you have a coil in the neighborhood, the neighboring coil or circuit 2, this field would stretch there, and then we would have the flux, which is on, okay, so due to coil 1 on coil 2 would be the same as K1 phi 1, 1, because the flux from coil 2 due to coil 1 would be depending on the flux in coil 1. And the mutual inductance, M. So if we are talking of coil circuit 1 to circuit 2, would be the same as phi 1, 2 over I1. This implies that M1, 2 would be equal to K1. Phi 1, 2 is K1, phi 1, 1, and this is divided by I1. Phi 1, 1 is L1, I1, so it is K1, L1, I1 for after substituting for, and then divided by I1. The I1s go, so this would imply that the M1, 2, that is the mutual inductance between the two circuits 1 and 2, would be the same as the K1 L1. Similarly, much as we say that M12 equals to M21, the M21 similarly, M21 would be the same as, here we see M12 being K1L1, so M21 would be the same as K2L2. And then M12 times M21 would be the same as K1, K2 times L1, L2. But we say that the relationship between a couple is the relationship. It doesn't matter whether you're looking at it on the side of the female or the male. If it is toxic, period. So, but M12 equals to M21, and we just say it is the relationship M. So the mutual inductance where M is the mutual inductance of a circuit. So that means M12 times M21 would be M times M, which will be M squared. So we would have that this implies that M squared would be equal to the K1, K2 times L1, L2. So we can group them just for purposes of clarity. Or we could take the square root of both sides and have M being the same as either plus or minus K root L1, L2. And this K we are introducing, which is equal to the root of K1, K2, is the money. Is the money in the marriage. So is the coefficient of coupling. If you got no money, you will have no coupling. And it's the square root of the woman's money is woman's money. Your man's money is their money for the whole family. So if you got no money, if K equal to 0, if you are broke, this means that there is no coupling. This means that do you know poor people who are coupling? Yes. This means that there is no coupling. Bread. Now, if there is some money, for K equal to 1, then M would be equal to the root L1, L2, because the other one would be unity. And this means that there is maximum coupling. So if you are rich, if you can buy gifts, bring a flower, a rose flower every day, take her out for fish, buy her a nice dress, then you have maximum coupling. So this means that there is maximum coupling. You can't fail to be a couple when you are rich. Yes. I wrote that there is no coupling. I'm for coupling. There is no coupling. In words I say it properly. True or false? That is. You couple with somebody who is broke?
No.
Why? Could be smart but broke. You don't eat smartness. Like
You don't eat just the brain.
smart, you don't eat their brains.
But you see,
I don't see. Their next brain.
see there is potential, someone can realize the potential.
And who was there for it for you to utilize your
You
potential?
raise your potential.
Okay, so we now want to see how these two coils are coupling, how they are able to communicate to each other. And then this was now the idea of Newman. So Newman made a formula, and Newman's formula was the beginning of cellular telephone communication. So that in a sense that if you have a coil and then you have another coil and then you have a current flowing in this coil and then you take the tangent to the circuit here or loop, whichever you want to call it. And then so if this is the current and then you have the DL, and if this is loop L1, if this is loop L1, and this is loop L2, I made this one bigger, and if it produces, it may miss out the other. So I want to make the other up a bit big so that whatever is produced down here is filled by the one above. So if I get the, okay, so if this is loop L1 and this is loop L2, okay, L2, L1, and then we have this as BL2. So if you change this current I1, once it changes, then it will produce a field which is changing, and this field would thread this other coil up here, and if their distance r, then we get an effect in this one. So some current can be loose. So I can draw another one just to show in details and be able to show that if this is the current I1 flowing in loop L1 and this is loop L2, then if you change this current I1, it will produce a field. So this is the field that is being produced by this other coil down here. So we have the field threading the other coil, and I just want to put another one here, then I can put the other one around here. So this is our B produced by the changing current. Of course, even with without changing current, depending on the direction of the current. So this current is going like this, you will have the field going up, even if there was no change in the current. So if you now change the current, then you change the field. When you have a change in field, then you induce an EMF. Then that EMF is how communication happens. When I call you, when I dial, I have induced, I have made this current here to change. And then this will produce a field, which should come to your phone. Now the issue is that this is B1, B1. This is B1 due to this other loop 1. So this is B1. And then I just want to first draw these things. I'm just drawing this flat to show that they are going through. Now, the concept is that when I dial, I produce a magnetic field. It comes to your phone. Now, when you have it can't just come to your phone. It is very small. That's why we get the masts, where there is a booster. So I produce an electric field, a magnetic field, and then the booster enhances it for a given cell. So when you have a mast, this mast here, or tower, whichever you want to call it, gives a certain area. So if this is the booster, somewhere you find there like that, of course with the lightning conductor. So this booster will give to a given cell, a given area. And that's why we call a cellular telephone. I don't know whether this is double. So we say it is a cellular telephone because it is served for a given cell. If you find a place where there is no mast, then this cannot be enhanced. That's when you look at the phone and then the network, what should be showing for network is 0, flat, because there is no booster. So you try to call, your magnetic field cannot go anywhere. It's a because there is no mast for boosting. And it doesn't matter whether you are the one calling me or I'm the one calling you. It's the same effect. You cannot say, for me I'm able to call you, don't worry, if there is no network, there is no network. And that's what we shall discover from Newman, whereby the formula is symmetrical. It doesn't matter whether it is this other distance here. It doesn't matter whether it is from here to here or from here to here. But the juju, like I tell you, these people make their juju work fine and they charge us. That's why I don't make calls. How do I pay for airtime? Air. Then I pay money. At least I can pay for internet because I can see photographs on WhatsApp, I can receive documents. But then I call Air, you talk. Some people, when I give them my UTL number, they say, don't you have like Airtel or whatever? Because there is Pakalast. How do I talk to you, Pakalast, as if I have money? If you have an issue, call. Tell me what you want, and I work on it. So, it means that this loop here, loop L2, if we look at the loop L2, it would be now experiencing a magnetic field from this running current. How do we get this magnetic field effect here? Which load do we use? Which load do we use? I know the first load, the one who came first. First come, first serve. I don't know the second and third, but at least I know who entered first. So which load do we use? If you have a conductor, carry I, and you want to know some distance from it, that magnetic field felt there, what load do you use? Bios bar. So, okay, bio and Savan. If that makes you comfortable. So from Biosivalo, then we can get some B1, and this B1 will be the same as mu naught I1 over 4 pi, and then we integrate over the curve C1 for coil 1, and then we have a dl cross R. This R is this distance here, and then over when it is R roof, what we get down here? R squared, because this one involves the other R, which would have made it cubed. So this is our equation 1, but this is just the magnetic flux density. But then when the current starts changing, then we now get interested in the flux. How much of the field lines are threading the area of the loop 2. So the magnetic flux threading circuit 2, the magnetic flux threading circuit 2 is to be phi flux in in circuit 2, which will be the integral of the felt magnetic flux density, which is B1, and then dot the surface area will be the surface area of circuit 2. This is our equation 2. Since there is mutual interaction between the two, put that the flux also is given by the mutual inductance between the circuit 1 and 2, I1, because this current I1 changing, and this one becomes our equation 3, where M12 is the mutual inductance. So we have begun from how we detect the magnetic field from a circuit by Biosivalo. When we have detected that field, we get to know how it interacts with the area to get the flux. And once we have gotten the flux, then now we can relate the two coils as being mutual to each other. And then the reason you get a ringtone is because a current is induced in your coil. And then that current is the one which induces the ringtone to start ringing, or a vibration. So that induced EMF, the induced EMF, or the EMF induced in our circuit 2, sorry, I love the gas and everything, but it's okay. There is when current I1 changes, so our induced EMF E2 would be the same as M12, then the I1 dt. But actually B1 was equal to the curl of the vector potential. So it's equal to the curl of the vector potential. Since it is B1, then it will be the vector potential in circuit 1. Now equation 2 becomes, I substitute in equation 3, I substitute for B1. So equation 2 becomes phi 2 being the same as integral over the surface area of loop 2. B1 is the curl of A1, and then dot S2. And we have a surface, and we are talking of the curve along the circuit. So we can change this surface into a line. So when you are moving from a surface to a line, or a line to the surface, what do we use? Stokes theorem. So using Stokes theorem, all this that is being taken as curve, we just take the vector and then we dot it with now a line. So that means phi 2 would be the same as integral S2, and then we have A1 dot dl 2. But vector potential, if you remember, but the vector potential A, sometime back, I think before I went away, A1 would be given by mu naught I over 4 pi, and this current here is the one in the circuit which is changing, and then we get the integral over this closed curve C1 dl1 over R. And then that means that if we substitute for A1, and we would get the phi 2 being the same as the integral S1, and then you put that. So I should have put the mu I on the outside, and of course we shall be integrating along the curve C2. So this is mu naught I1 over 4 pi integral. We are within a flux affecting the area 2, so it will be curve C2. And then we have in this other part of A1. So this is mu naught I1 this, the L1, and then in this one here. This would be C1, and then we have dl1 over R. This is typically algebraic gymnastics. It's not much that I can add or subtract other than following the substitutions and the like. And then this would be dot. This was A1, so it will be dot. So the whole thing is covered here like this, with this parenthesis, and then we'll be having dot dl 2. From equation 3, I don't know where it is, but you have it in your notes. From equation 3, then we have this phi 2 being the same as mu naught I over 4 pi, and this is I1, integral over curve 1, integral over curve 2, and then we have the dl1 dot dl2, and then all of this will be divided by R. And this should be equal to the flux phi 2, and phi 2 was the same as M1 2 I 1. This qualifies to be our equation. So we can write the initial inductance. Thus, the mutual inductance between these two coils would be the same as, so I1 would cancel, and then the mutual inductance would be the same as the mu naught over 4 pi. I1 cancelled, so we have integral along the curve C1, integral along curve C2, the L1 dot the L2 over, and this is our equation 5. If you look at it closely, it doesn't matter whether you first integrate along curve C1 or along curve C2. Also, it doesn't matter whether you get the L2 dot, the L1 dot, the L2 is the same as the L2 dot. So this equation here is symmetrical. That's the reason why it doesn't matter if I'm the one calling you or you are the one calling me. The phones will ring. If we have a cellular tower which is providing us the boosting, our phones will go through and ring. So we conclude, we draw the explanation or conclusion of what this means and say that equation 5 is called Newman's formula. Equation 5 is called Newman's formula. We start from the only challenge on this is when you start remembering the A1, the vector potential. But we start by understanding how we detect the field away from the coil. After defining that, then we do the what is now the flux, we get it, and then we talk of the mutual inductance. Note that M21 equals to M12 equals to, and this is due to symmetrical form of Newman's equation or formula of Newman's formula. It's symmetrical. Symmetrical meaning that it doesn't matter whether you have this one this side, it doesn't matter whether you start with V2 and L2 dot L1. The dot product, how do you say, is the associative or universal? Now, M12 is purely geometrical. Is purely geometrical. I was using the example, which is very funny. That which is a purely geometrical quantity. It all depends on the Nyash, for example. Having the that's the geometry I'm talking about. Having to do with sizes. Having to do with sizes, shapes, and relative positions. And relative positions of the two loops. So we have finished preparing for the course. We have just been trying to lay ground for electromagnetism. All this law. So now we are going to start electromagnetism. And the next part is the Maxwell's equations. So we were doing nothing. Yes. This is now when we are doing the course. We are just trying to understand how does the current flow in steady currents, how do the dielectrics behave if we are going to make the conductors for transmitting the electromagnetic waves. Now we're going to understand the electromagnetic waves and how they are propagated. And this is under Maxwell's equations. Maybe next year we'll just start from Maxwell's equations. Read about the other parts. No problem. You will not be there. So Maxwell's equations. I used to give cassava for people to tell me the full name of Maxwell. This time I have very small cassava, but it's new. These are 2 pieces of cassava. Don't Google, Fred. What are the other names of Maxwell? Don't Google. You have already Googled, so you are disqualified.
The word is here.
It is wording. You are also Googling. I saw the phone just down there. And even if you deny, when I look at the history, I will see that you are Googling. But you can go here. He has no phone.
Yeah, we are smart.
He has got square. Oh, when he has a cartouche, you can't do. Anyway, just you can go here. I'm not giving you my cassava. This one is protecting the. So James Clerk Maxwell, pardon? He tried to make sure that he revises that he revised. When I was in a taxi one time, I was sitting near a lady. So when I had the 1K, she had a 500, and the general was for 500. So I wanted to get the 500 from her, and then I give the 1,000 to the conductor, and she refused. She wanted to give it to the. So I asked, what is the reason? I said, my friend, they can put juju and they take away your business. So I laughed. Now I used to give out money on the traffic lights. 1,000, whatever, the beggars. They say, never do it again. Some of those have a bad heart, they will go and dry your pocket. So if I am to give somebody money, like these old women or whatever, I give a 50K. They told me that with the 50K, when you make balance, it doesn't work. If you change. So I lose the money, but know that I'm safe. So these things of giving 2K, 5K, no. 20K and above. So there are people who used to think I'm generous, but I was avoiding problems. So then, the known basic laws of electricity and magnetism before Maxwell were the known basic laws of electricity and magnetism the life was moving on normally before Maxwell. Just like it has been moving on very well until when I am coming about and questioning why we have the current flowing in a particular direction. Before Maxwell, did some work where, so we said if we diverge an electric field within a material, then we are concerned about the charge density and the permittivity. Or we can narrow it down or generalize it to the electric displacement vector. So if we look at the way the electric displacement vector is diverging, then this one would be equal to rho. So that is the first law before Maxwell. This is within electrostatics. The corresponding result for magnetic field, the corresponding result for, I know sometimes when I teach, I don't follow what they taught me to teach like. You know, like you write on the board when you are quiet, muted, and then you turn and then you say, note. But we shall never finish if I am to do that methodology. So when I shared my videos on YouTube one time, some guy said, but you are talking to the blackboard. I know, but you are beyond that level. All I'm doing, I'm avoiding dictating. Because some of you keep saying, come again, as if I'm going to come. So, the corresponding result for magnetic field is that when we try to diverge the magnetic fields, then we break them. And when we break them, so we get 0. So, equation 2 means that the field lines are continuous. You try to touch them, they disappear. Equation 2 means that all the magnetic fields are continuous. You try to touch them, they disappear. Then there was Faraday, who did some experiments. Michael, with some violation of history, he came up with an integral form of Faraday's law, as well as differential form of Faraday's law. So, Faraday's law of electromagnetic induction we say that when you try to curl, these are electric field lines. When you try to curl them, if the field lines are static, they disappear. So you won't find anything. So that's why we say the curl of E equals 0 for electrostatic fields. But if you are able to generate this current by induction, you'll be busy. It's a toxic relationship. So you are busy trying to curl the E. This is the toxicity. And then this one is making the induction reduce. That's where the negative is coming up. Yes, you are sustaining the production of the electric fields, but you are straining. It's a toxic relationship. So that's why we put a negative here. And then relatively corresponding is Ampere's law. Ampere's law in differential form. Ampere is a current, so in differential form for steady, I want to see whether I am about to reach the top of the hour. For steady currents is given by the curl of the magnetic fields And this would be the same as if you try to curl the magnetic field lines, that means you make them concentrated. And when you make them concentrated, then you produce some current. And when you consider the area in which you are concentrating these fields, which you are carrying, then you have the current. And then this one becomes equation. This one is equation 3. This one is a bit hanging. So Maxwell's did some correction, some adjustment. So this equation needs to be modified. This equation needs to be modified in order to cater for varying fields. In order to take care of or to cater for the varying fields. I'm sure you are done with the course which you normally used to go to at 5.
Yes. Yes.
So I'm going up to 6.
It's okay.
Huh?
Go to 7.
I can go to 7.
Yes.
Good. I'm okay.
Go to 8.
Now, if we took the divergence both sides, then we would have the taking the divergence of both sides. See, I didn't sleep. I started traveling on. We were picked at the guest house at 1 a.m. No, at 2. We bought and we reached here at 11 p.m. The next day I was in the garden. I had spent some time without looking after my health. Sunday I did chores. Monday I was here in class. So I think I need some good sleep. And I wake up at 4:30 to come here. So that's why I cannot go to 7. So the divergence of the curve of H is equal to the divergence of, and what would this equal to? What would this equal to?
0.
Why? Because what?
Because J is equal to.
We get the idea that the divergence on the Maxwell equation. Then we assume that
Divergence of J, when you have charges in a given area, in a given volume, surrounded by a given area, when you diverge this, when these charges start escaping, that's the divergence of J. We say that will equal to the rate at which the charge is being lost, which is minus Carrero by. But now why is it equaling to 0? I don't know how you can use the math. Those of you who are using math, eventually when you end up getting the divergence of H, then it gives you. So who can expand for me the divergence of the car? Yes. Yes, we have the divergence of the curl of H. How can you expand it? Simple. You are looking for the identities. Anyone with identities? I don't have Mwele here. Yes, Mwele. I don't have Mwele here.
But I think the statement is right.
I know it is right, but I want you to get it. Anyone with the identities? I'm sure the divergence is it associative or dissociative? You can now take the divergence of the gradient operator. Okay, so you can get gradient operator dot gradient operator, which becomes grad square, and also you get the divergence of H. And when you take the divergence of H, because B is equal to mu H, when these are magnetic fields. So if divergence of B equals 0, so is divergence of H. Okay? So from the equation of continuity, whereby the amount of charge escaping constituting the current density is equal to the rate at which the charge is being lost minus Carino by Kali T. From the equation of continuity, the divergence of J is equal to minus Kali rho by Kali T, but we have already said that the divergence of J equals to from this equation. And this is true. This is true if and only if the charge density does not depend on time. It is independent of time. So, if that is the case, then we can now bring in the Gauss's law. Yes.
So if I want to sketch, where was the contribution of Maxwell?
We are moving, don't
Let's say it before.
relax. This one, we are still working on before. So once we state these equations and use them, we shall find that he was one of the geniuses that have very task people to like.
But usually it's very
Yes, you can, there is food in the market, but one woman will cook it and it becomes tasty. So you can't say the food was there anyway. You get the point? The equations were there of electricity and magnetism. They were being used as they are. But he came with another perspective, which we are working on, don't worry. So using Gauss's law, patience. Huh? It pays, but it pays. Using Gauss's law, which is the divergence of D equaling to rho, the equation of continuity becomes the equation of continuity becomes divergence of J being the same as minus Kali rho by Kali T. Rho is divergence of D, so it will be minus Kali by Kali T divergence of D. And this would imply that divergence of J is equal to divergence of, we can put the divergence on the outside and then we get inside as Kali D by Kali T. And then we can put together this side since they are all divergences so that they become one divergence of the J plus Kali D by Kali T. This would be equal to 0. Thus, we would comfortably say that what was equal to 0 here was that the divergence of the curl of H now will be equal to the divergence of the J plus Kali D by Kali T. It's about divergence. If you are diverging both sides, you are not doing anything. If I buy sweets for the children, same sweets for the two children, they don't feel any difference. They feel like nothing has changed. Yes, they have the sweets, but there is no difference. But if I bought one more, they would feel like they are more loved. So we are doing divergence both sides, meaning that we are doing nothing. So we can write what we are diverging to be the cause of the equality. So therefore, or hence, we have the curl of H being the same as the current density plus the Maxwell's correction. This is equation 4. And this is only true because of this rate here. This is only true for time varying, for fields which are changing with time. So for time varying fields. So now we can summarize what Maxwell came up with. And then after that, we do the algebraic gymnastics. So in summary, the video which I shared, I think I had just come from Pakwachi and slept in the bus, and then the next day I was in class. That's why I'm in that shirt. So I was tired like I'm tired now. I don't know why I have to teach this part when I'm tired. So in summary, the field vectors, because we call them magnetic field, electric field, magnetic field intensity, magnetic flux density. So the field vectors E, H, we let them put in the order. E is related to D, then B is related to H. Satisfy everywhere. Satisfy everywhere. The set of Maxwell's equations. The set of James Clerk Maxwell's equations. and this is in Mara. So on next Friday, I was supposed to do it this Friday. I was supposed to have a Zoom meeting as I criticized the O-level questions. So I postponed the next Friday. So I want to do it, I hope I will be fine. I want to do the Zoom meeting and tell people that stop making our children workers for making chapati and cakes. I saw one school sharing a photo that our kids are doing animal husbandry. They are making hay, cutting this grass and arranging it together for the cows. That is for Shamba boys, not for somebody who goes to school. So I hope I will be able to leave happily after that Zoom meeting, because I want to be very. I will share with you the link when I'm ready, if you want. Dr. Taku? So the equations we have written are that Maxwell repeated Gauss's law. And Gauss's law was the divergence of E equals to, this is equation, this is Maxwell's equation 1. Correspondingly for the magnetic fields, the other equation has no name. You can choose to take it if you want.
Yes.
And the divergence of B was equal to, and that is equation. And then Faraday explained that the more you try to curl the electric field lines, that reduces your efforts as you are trying to generate the current. So Faraday's law, the curl of B equals to, the curl of E equals to minus Khalid B by Khalid. This is the electromagnetic induction which is producing the electric current, which is responsible for these electric fields. When you start bending these electric field lines which are being, electric fields which are being produced, then that reduction is depicted here. You are generating, but you are reducing by current. And this one becomes equation. And then finally, we get the Ampere's law, which was the curl of H equal to J, but with Maxwell's correction to take care of the time varying fields. So this is Ampere's law with Maxwell's correction. So meaning that the curl of H is equal to the current density plus the rate at which you are having the electric displacement changing. So this is equation 4. Of course, just to define the terms, the symbols used, they can carry the same meaning in physics, but that is not possible. At one point we used rho for volume charge density, another time we used rho for resistivity. And at another point we used, I think the other ones are okay. So where rho is the volume charge density, J is the current density, the field vectors, B is the electric displacement vector, B is the magnetic flux density, E is electric field density. So let me just put them in order. D is the electric displacement vector. D is the magnetic flux density. E is the electric field density. And then H is the magnetic field density or field strength. Magnetic field density. And the symbol I have left. So the notorious question is always state Maxwell's equations and define all the symbols used. Huh? There? There? Which operator? The Del operator? The Gradian operator is an operator, it doesn't make sense. I know it is Gradian operator, yes.
That's the order matter when you ask that question. The order of arrangement of those equations.
Do you think it matters? So you can say equation 1 is curl of H equal to, you are in trouble. Equation 1, this is the order of electrostatics. From electrostatics, we go to the magnetic fields, and then we try to tingle with the electric fields, and then finally, again try to tinker with the magnetic fields. So, when you have these fields, you have an electric and a magnetic field. So you have to hustle. You have to curl them. They are here. They are in your deck. So you have to curl them and fit them in this wire. So we're going to do that. So I need these equations whereby the divergence of E, then the divergence of corresponding magnetic field, then the curl of E takes away your efforts of producing the electric fields, and then the curl of H will give you the JS. Remember we had JS, which was the eddy currents, and then plus this other current in here, the dB dt. But before we curl them, we need to add something on a few things. So the relations for isotropic means that a material has the same properties everywhere in all directions. Linear and homogeneous media, then we can relate these field vectors. The field vector D is related to E as epsilon E, which sometimes can be written as epsilon naught, epsilon r E. D is related to H by looking at the permeability of these fields, which sometimes we can go to say this is mu naught, mu r, then H, where the mu R is the relative permeability, and from microscopic form of Ohm's law, J is equal to sigma E. Where now we got a different, we got an additional symbol, which is not surface charge density, but now is the conductivity of the medium, where sigma is the conductivity of the medium. Now we are ready to go. We are ready to feed these field vectors within these wires. Yes. Do you know what?
Like if they say that state the Maxwell's equation for a linear isotropic or a homogeneous media, we can substitute those field vectors inside those Maxwell's equations.
No. You don't have to put that divergence of epsilon E equal to rho. You state the divergence of B equal to rho, divergence of B equal to 0, curl of E equal to minus Karibi by Karibi, and the curl of H equals to J plus Karibi by Karibi. That's it. You gotta write the vectors like this. Like this single one.
I thought that maybe for that case, it's just vector and then substitute it there where it's D.
No. This statement here is to show that the B you are seeing, the other direct side, actually has a component of the permittivity and the electric field density. So when you are now interested in understanding more of your medium, which you are using to transport the electromagnetic waves, then you must be aware. For example, we have these banana cables with these cylinders and with a dielectric in the middle. That dielectric is the one which is under the epsilon, the permittivity. And so you need to know what is going on and know how that will affect your signal. You have seen that you are watching a movie and then when you put a banana cable, the things develop rise. And so that means you have a problem in your medium which you are using. So, the other ones are okay. These two are just like information. But that means if we can now squeeze these and curl them again, if we plug this in the deck, and then we have to curl them, and then make sure they move in these small wires. The pictures you see on the TV screen for a movie, they all go through here. So they have to be curled. So taking the curl of equation, this is equation 1, 2, 3, 4. So taking the curl of equation 3, then we would have that the curl of E is equal to the curl of the minus Karibi by Karibi. Anyone with identities? What is the identity when you got the curl vector A? Or so she has it in the head. So that is the divergence of.
Inside we put the ring there. That cuts him. Open brackets. Operator open brackets.
Okay, so like this.
Then the gradient dot.
So divergence of the vector.
Yes. Minus.
Minus.
Divergence is squared.
grad squared.
Grad squared
Grad squared
of E.
E, and this should be equal to this other side here. And B from the relations for isotropic linear media is equal to mu H. So that means we will have the curl of minus, okay, this is minus minus Kali by Kali T, then the curl, sorry, mu, so we have a mu outside. So this one will be minus mu, and then we have H. Is that okay? Good. So this would imply that we have grad divergence of E minus grad square E being the same as, now we can put the minus outside, the Kali by Kali T outside, and now we have the inside being the curl of H. But from equation 4, curl of H equals to J plus Kali D by, and J equals to sigma E, and D equals to epsilon E. So I plugged in. So this would imply that the grad divergence of E minus grad square E is equal to minus Kali by Kali T. I forgot a mu. There is a mu here, so there is a minus mu here. So there is a minus mu here. Kali by Kali T. So the curl of, so this would be J plus Kali D by Kali T. Let's take step after step. So this would imply that the grad divergence of E minus grad squared E is equal to, so I can expand. This would be minus, can I substitute for J at this point?
Yeah.
So I will say it is minus sigma mu, and then I have Kali E by Kali T, and then I have minus, D is epsilon, so it will be mu, epsilon, so I can put it in the order of epsilon mu, and then this Kali here will be combined with this, I get Kali squared E by Kali T squared. Are we together? Okay, so if we are together, then we say that this would imply that I think we've done almost everything. So this is an equation in this is an equation in field vector E, if you look at it. But the divergence of E equals to rho over epsilon. If that is the case, that divergence of E equals to rho of epsilon, and we are looking at the, if of course E is, epsilon is a constant, okay?
Yes.
And we don't expect the charge density to be varying with the X, Y, and Z to be diverged by, to be worked on by this gradient operator. So this one here, which will become the gradient of rho of epsilon minus grad square E equaling to minus mu sigma Kali E by Kali T minus mu epsilon Kali squared E by Kali T. This is differentiating a constant. When you differentiate a constant, what do you got? 0. So this one will disappear too. 0. So, gradient rho of epsilon equals 0 since rho and epsilon are constants. So, I remain with grad squared, and then I can put it this side, then equals 0, but also arrange it with the same orders, the order of differentiation, so that it becomes a very nice looking equation. So, thus, we have an equation that grad squared E minus, when I put this side, it becomes positive. So minus mu epsilon Kali squared E by Kali T squared minus the mu sigma Kali by Kali T equals 2. So this is an equation of the wave for the electric field. So when we curl the E again in equation 3, then we would have assembled our electric field to move following this equation. So I was not labeling these equations. I don't know whether I can label them, but let me try to see whether I can label them. Just for purposes of so we have the one which we were taking the curl of equation 3, then we have equation 4. So if you take the curl until here, this will be equation 4 prime, because the equation 4 is the fourth Maxwell's equation. And then this one we are getting here, this equation here we are getting is the equation 5 in the notes, just to make sure that you follow.
Excuse me.
Yes.
I would like to know when it comes to Maxwell's equations. When I try to state the Maxwell's equation for a conductor, is it the expression whereby rho is taken to be 0?
Why don't you relax? We shall look at the propagation. We have the section for Maxwell's equations in conducting media. So we have grad squared E minus mu epsilon. I'm trying to Kali squared E, Kali T squared minus mu sigma Kali by Kali T equaling to 0. So this is equation 5. Taking the curl of equation 4, we now try to curl the magnetic field. Sorry, if I rub quickly, these things out of the way. Yeah. And soon they will be, whatever I wrote here soon, tonight, if power is there, even if it is not there, I have power at home. I never fail to get power. It is here where they joke, and even when I told them, they made sure my lecture has power. Do you sometimes believe me what I say? No. You refuse to believe at your own risk, and Fred knows. Fred knows. So we are taking the curl of H, which is equal to the curl of the J plus Kali D by kali t. We already, then we say, but because it is here where things are not reduced. But J equals sigma E and D equals to epsilon. So we say that this is grad divergence of H minus grad squared H being the same as the curl of H, sorry, the curl of J, which is the sigma curl of E plus the carry by carry, sorry, the epsilon carry by carry T, the curl of E. And but the curl of E is equal to minus, but the curl of E, the Faraday's law, you hustle with reducing, whatever you are generating reduces, which is the same as minus mu kali H by kali T. So then but from Maxwell's second equation, the divergence of B is equal to 0. B is equal to mu H. So the divergence of mu H also equals to 0 because you divide by mu both sides. So we eventually get cancelling mu's and then 0 over mu becomes 0. So this one is equal to 0 from the law. The other one was equal from, this one is equal to 0 from constant, and you are differentiating the constant. Mark that. On this one of E, divergence of E is replaced with sigma, with rho of epsilon, but that now becomes a constant. You cannot differentiate the constant. So that's how it goes to 0. But this one, it goes to 0 because the divergence of B, which is equal to the divergence of mu H, equals to 0. So we remain with this part here, minus grad squared H equaling to the sigma, this is minus, so this is mu, so this is minus sigma mu, and then we have a kali H by kali T. I'm substituting for B straight away. And then we come here, we have minus epsilon, then the mu in the dB, and kali B. So we now have this combining with the kali B, the minus kali B, sorry, because the minus is here. So we have this kali by kali T combining with the kali B, so it becomes kali squared H, because the mu for B is here, then kali T squared. So we arrange it properly, and when we arrange it properly, on rearrangement, then we get grad squared H minus epsilon mu kali squared H kali T squared minus sigma mu kali H by kali T equals to, this is our other, so this is how the H will propagate within these wires here. After we have squeezed them at this level of the banana cables. And so this should be equation 6. The other whole equations are not labeled at all. For if you go to Mwele, you should be able to do 6. So I have 6 here, grad squared H minus mu epsilon Kali squared h, Kali T squared minus mu sigma Kali h by Kali T equals to 0. So this is within this wire. So how about if we squeeze them in the router and then we use the antenna? This is our router, and then we use the antenna of the router here to squeeze them to space. And then they start moving in space. How would they move? So how they would move is that in free space, in free space, in free space, mu will equal to mu naught. Epsilon will equal to? Which one is there? Which else is there? There is, which one is rho? So sigma, what is the conductivity in free space? So equations 5 and 6 would respectively become equations 5 and 6 would respectively become, so this baby here, these babies are disappearing because of the sigma. And when they disappear, then we remain with the grand squared E minus mu naught epsilon naught Kali squared E Kali T squared equals to, and then grand squared H minus mu naught epsilon naught Kali squared H by Kali T squared equals to, and this will become equation 8, and this one will become equation, say, 7. Now, it is becoming sweeter. It is looking nice. And if it is looking nice, then these equations are referred to as wave equations. So, and if I just want to make sure that you can follow the notes, since I have finished the right gymnastics. I'm sure you can derive these things. It's about just mathematics. So these are wave equations, which move with the phase, which move with the frequency, which go through a medium. Some media have refractive index. Some media have conductivity. If, for example, is water. To measure by a few. So the equations 7 and 8, equations 7 and 8 are referred to as wave equations. Now, in your classical mechanics, you studied waves. And we can compare the wave equation for the waves you studied in classical mechanics, and then try to see something now. So comparing with the general, or what we normally call the classical, the one which we did in classical mechanics. Wave equation, which we can state as grad squared phi minus 1 over v squared Kali squared phi by Kali t squared is equal to 0. And if this is taken as equation 9, we conclude that if we compare these two, this is grad squared E, and it is the same. So it means that this part here is equal to the 1 over, actually this other part only is equal to 1 over V, which is the phase velocity. And we know mu naught as 4 pi times 10 to the power negative 7 on meters per meter. And we know epsilon naught, which is 8.85 times 10 to the power negative 12 joules per meter, or newtons whatever. So we can calculate and see what speed these two babies will move with after we have tried to put them in a router. So we want to see how they will propagate in space. So we conclude that at any time, that is valid in electric, that is the Kali squared by Kali t squared, that's the time value variation. Or magnetic, the Kali squared h by Kali t squared. Fields are propagated with the same speed. Because this one has this speed, this one also has this speed, if you compare with the classical equation. And this same speed, which is v, is equal to the speed of light, which is the same as if mu naught epsilon naught is equal to 1 over v squared, then that means that v squared will be equal to 1 over the root. So this is equal to 1 over root epsilon naught mu naught. Who has a calc? This is equal to 1 over root 8.85 times 10 to the power negative 12 times 4 pi times 10 to the power negative 7. Do that and tell me what happens. And I'll tell you, I'll tell you why Maxwell made a revolution that we are enjoying today. Najuma, they say you got a calc. Do the thing, do the damn thing and tell me.
It's 8.
Huh?
It's 8.
How did you collect the nearest? Yeah, do. 2.9. It's 2.9 something. 9 some then times 7 by 8. Anyhow, which is the same as 3 times 10 to the power 8 meters per So these two babies can move at the speed of. So when you are here and you are talking to your friend in the United States, when you say hi, immediately you see the blue ticks. When you are here in Uganda and then you say hi, it doesn't matter whether somebody is in Chikoni, whether somebody is next to you, these damn things will move at the speed of. And Makoni went ahead and tried to use transcontinental radio communication. He tried to come up with the first radio. Although Makoni was using the ionosphere to make sure that he can transfer these radio waves, but that's how now Maxwell's work became useful. I respect him for that. It's Gauss I have problems with. Are you still fresh? Yes. The way you answer is the way you answer is very sarcastic. Yes. Okay, so we got 2 lectures in remaining. No, I'm not feeling well. So I know it is still we still got like 13 minutes, but I didn't wanna go into these babies of phase waves. I wanted you to go when you are satisfied that now we are having the electric and the magnetic field vectors moving at the speed of. Using Maxwell's approach, we've been able to establish that. So I feel like we end here, so next week, even if I stopped here, I'm sure you'll be able to understand whatever is remaining. Why? I am on YouTube. No problem, I'm here. So we shall move on from here on next week. But if you are tomorrow, we thought we could use Wednesday.
No, we are fixed. We have it.
I am still talking. Even if you have what? Of what?
Agriculture.
What do you do? No problem. So but I'm very confident that even if I came and explained like now you know how this stuff came about. You know how the identities were used in whatever. Then the other part is also when we go to conducting media. Then it's the same thing. You do the same Maxwell's equations, do the can, but now you are using the media. The only thing that I got to explain more, which I know that is tricky, is the one of reflection and refraction of the wave. This is when I do something that I'm the only one who does it in the world. When I have the electric wave, and then so I'm able to show you that there is a horizontal and a vertical. And Ivaio is busy doing like this. You have to make sure this is horizontal and this one is vertical. Then you do it at once. So you do this, so you start. You do this. That's why I said I'm the only one who does it in the whole world. So I'm confident that we shall be able to finish the course fully. Then test 2, we can do it on a Sunday.
Yes.
Yes.
No, I'm kidding. I can't come here on a Sunday. But let's focus on finishing the course. And maybe also mark. And if you see your marks, you can decide whether we take one test
Yes.
or we can take two tests. But the rules of assessment and university, I must give at least two tests. So don't worry. If we see where for example, we covered a lot of stuff. These old pages here.
We can do an objective break now.
We covered all this electromagnetic induction from yesterday. So the remaining part here is very small. Just symbols. Doing a test is not so hard. I can even let you set your question and you answer. I am the boss. I say send your question and answer it, and then you sweat. Even to send the question out will be a problem. Now I'm kidding. Let's first see how Monday goes. If we have gone well on Monday, then we can schedule it. So those of you, you have to make sure you are attending these days for any eventuality. Any complaint or suggestion? The party we can have next week, but we can have it on. It has to be within the